For this reason, we introduce some bridge nodes. The idea is a simple idea. In this case, in this figure, we show the application of this scheme with two deployments. So nodes number 1 are from deployment 1. They use a separate pool of keys, independent of the scheme. All type of schemes can be used. And nodes number 2 are of the second deployment, using another pool of keys. And as I said, they cannot talk directly to each other because they use different keys. And we use some bridge nodes, 1, 2 here in this figure, which one have keys from both deployments. And now, because these bridge nodes are much less than other nodes, we reduce a lot the probability of being captured, and also we reduce a lot the probability of compromising keys of other deployments. So there are some assumptions. So the enemy can randomly take all kind of nodes, take over. Now, so these bridge nodes could be normal nodes or could be stronger nodes in the sense that they might have more memory or more battery, and of course that will improve the security. Here we have some analysis. I won't go in details. Actually, this is a published paper. You can get in my web page. The only thing to show you that here is the probability of keys being compromised between deployments. And as you see here in the formula, if the pool of keys has no keys in common, then the probability is smaller, much smaller than when you have the same pool of keys. So here are some experiments, some simulations, in which one we apply our scheme over different other schemes. So this part here is regarding random key deployment predistribution, and this is Q composite random predistribution of keys, the other figure. And this is the kind of red one is the scheme itself, and here is when blue one when we apply our scheme, and this is the link percentage of links compromised. And you see now that the first deployment, the number of links compromised is the same. Of course, there is one deployment, but then you have 2 deployments. You see it's almost half of the keys are compromised using our scheme, and third deployment more, the advantages keep building. As I said, the interesting part that you can apply this to this scheme to any other type of security symmetric security scheme. Here we talk about the overhead. Of course, this improvement in security cannot come for free. Basically, using intermediate nodes, the number of hubs it's increased, and you see, this was using the original scheme. When you apply our strategy, of course, we get more hubs for each connection. That's the price to pay for security. Now here we analyze the role of bridges, these nodes, intermediate nodes, and the more bridges you have, better connectivity you can get. That's obvious. Now let me move to another scheme, and this scheme is when you have combination of fixed node and mobile nodes. Could be a situation like this. You have sensor nodes which gather information, and then you have some mobile nodes like cell phones which go and get this information. Again, how to build the security? And most of the proposed schemes, they use the same pool of keys for both stationary and mobile nodes. Again, we might have problems here because, for example, the enemy might be able to get some keys here. And because it's the same pool of keys, also they will get communication from mobile nodes, communication from other networks. So basically, security is compromised over the whole set of nodes or networks. So basically, to change this, to improve this situation, this is what we propose. We propose 2 schemes. In the first scheme, we create a separate pool of keys just for mobile nodes, and some of these keys also are given to stationary nodes. And of course, then each sensor network will have its own pool of keys to talk among each other. And in this way, we can improve a lot the security. So basically, when they capture keys from sensor networks, because sensor networks are much more vulnerable, the communication of mobile nodes won't be compromised, and the communication of other sensor networks won't be compromised. So actually, this increases security, and compared to the other technique, which I will talk in a minute, it has less overhead. The other technique is like this. It's called segmented key pool. Each sensor network has its own pool of keys, and the mobile node picks up some of the keys from each one of them. Okay. Again, we separate here keys between sensor networks, and that will improve security. The problem with this scheme is that it's not very scalable. Basically, if the number of sensor networks is huge, then you need a lot of pools. Okay. On the other hand, provides better connectivity, and this connectivity is paid by overhead, and also it's less secure compared to the previous scheme. Okay. Here are the metrics. We define the metrics: security, connectivity, and overhead. Security is probability of a link being captured by the enemy. Connectivity, probability of mobile nodes establishing secure links. Overhead, it's how much memory you need, basically how much keys you have to keep. And here are some results which compare schemes. So basically, here's links establishment versus overhead. And as you see that segmented key pool provides better connectivity and paid by more overhead. Security-wise, the segmented key pool, it's less secure than separate key pool, the scheme in which one you have just one separate pool of keys for mobile nodes. And here's the relation between overhead and security. Again, this is the blue one, it's segmented key pool, and the other one is the separate key pool. And as I said, the separate key pool is more secure. And as I said, the segmented key pool is not very scalable, because as you see, if you have a lot of sensor networks and you have to have for each one a segment, the link establishment percentage goes down, so it's not very scalable compared to other ones. So basically, there are trade-offs between both schemes depending on the application you need. Now, another scheme which really I like in particular is this one, in which one we use cellular phones in emergency situation. So when something bad happens, like hurricane or terrorist attack or anything, most likely all communications are disrupted. All wires are cut, towers are down, and it's a really bad situation. Now, in this bad situation, and people die about this, and thousands of people have died in many cases. Even though we cannot talk, we have some devices, we have cell phones, which are very powerful devices, which can be used. The only way is that we have to change the way they communicate. Of course, they cannot talk anymore with towers, which are down, but we can make them talk to each other as ad hoc devices. They are very powerful devices. They can talk, cover a lot of distances. They have good batteries. So why don't we use this? So when everything is down, we start talking with our cell phones with each other. And we can use it for a lot of good information to go along. We can use them to talk to other areas of the network which the cellular phone could be working, or with the internet. So we are working in this area. We have designed the communication part of it, routing protocols and the rest. But also we are worried about security, because in this situation, yes, good people will use it for a good purpose, but might be bad people who might use this situation to create even more damages. Think about some terrorist attack. On top of whatever they might blow up, they may also spread the wrong information, sending people to wrong places. Okay, so basically security is very important. Now, one thing we try to achieve here, the first thing, we would like to achieve non-repudiation, so basically authentication. Now we know that authentication in ad hoc network is not easy.